Section 1.3 is vector equations. So we're extending now from our systems of linear equations. In 1.2, we went into matrix equations, or a matrix representation of a linear system of equations. And now we're stepping into the vector representation of that equation. So these are all one and the same object, a linear system, a matrix equation, or a vector equation. So they're just different notations for essentially the same thing. So we'll start with just a basic definition of a vector. Vectors are used throughout physics and mathematics in general, and they have a lot of different interpretations and meanings. This won't be anything inconsistent with those, but we'll simply think of a vector, or a column vector is how we'll write most of our vectors in this class, as an n-tuple, where we just have n entries in a single line of a vector. So we've written most of those horizontally, but we'll think about a column vector written as v1 all the way down to vn for its elements for the vector v, using that arrow hat notation or bold print when it's in text as our indicator that this is a vector. So two vectors are equal if and only if each of their corresponding entries are equal. That's a pretty easy thing to see. So if v was equal to u as vectors, then that would mean that v1 is equal to u1, v2 is equal to u2, all the way down to vn is equal to un, and those two vectors would be the same. We won't think too much about the geometric representation of these things right away, because we can get enough at just treating these things like tuples. So the sum of two vectors is obtained by adding the corresponding elements of the vectors. So if we have v plus u as vectors, then in order to get their sum, it was just v1 plus u1, v2 plus u2, vn plus un, all the way down the line. And we'd have a new vector that's the sum of v and u. And it turns out that that will match the exact geometric interpretation that one might be familiar with in regards to vectors. The scalar multiple of a vector. So if we multiplied u by the vector c, so c is we multiplied the vector u by the scalar c, the real number c, then it would look something like this. C is times the vector u1 to un are our components. And all that would look like would be component-wise multiplication of that scalar, c times u1, c times u2, all the way down to c times u sub n. So pretty straightforward calculations with these things. And we'll see some direct examples of this in just a moment. So the difference of two vectors is simply, well, we write u minus v as vectors, and that could be expressed as u plus negative v. And this is really the same as saying this is the vector u plus the vector formed by multiplying -1 times the vector v. Okay, and by using our defined addition of vectors for this portion of it, and our scalar multiplication of vectors for this portion of it, we would arrive at the difference of these two vectors. But note that we could also write it's u1 minus v1 all the way down the line to un minus vn. It's a very nice, clean type of calculation. So if we take a geometric interpretation for just a second here, if we add two vectors, arbitrary vectors a and b together, there is a geometric way of thinking about that. Most vectors we think of as starting at the origin. So we'll call this the vector A, and this will be the vector B. They both have initial side at the origin. That's the non-pointy side, right? And then the arrow side is the terminal side. So if we added these two vectors, it's the same as traveling one vector and then another vector. So we use what's called the parallelogram rule. So this is another copy of A, it's just gone tip to tail. So here's the tip of B, and then the tail of it is A right here. We could similarly arrive at the same place by going out A and then along B. So we arrive at the same point, and the resultant vector, the point that we arrive at from where we started, is the vector A plus B. So this diagonal in that parallelogram is the vector A plus B. Okay, that's just harking back to a geometric interpretation of these you might have seen in a Calc 3 class or in a physics course dealing with vectors. We'll do a little bit more geometric interpretation, but this gives you the basis for interpreting this onto coordinates for any questions that might come up regarding that. But mostly we're going to focus on properties of vectors and what we can do with them regarding solving linear systems of equations and what it means in terms of these column vectors. So for some positive integer n, we'll talk about this space Rn. This is the real space Rn. So it's the space of vectors that have n components in them, each of which component is a real number, not a complex number, but any real number. Those are irrational numbers, rational numbers, integers, and so on. The zero vector is a special vector written in bold here, or as a zero with a vector notation over it. It's the vector containing all zeros as entries in whatever space Rn that we're talking about. So properties of vectors that are pretty obvious to us, and we actually probably just saw this in the last geometric interpretation. The vector a plus b is equal to the vector b plus a. If we go back and look at that, that's because this is a plus b, and this vector is b plus a, and they both arrive at the same place, and we end up with a plus b, which is the same as b plus a. We could write that there. That's a geometric intuition. Proving it really boils down to writing out the components of each of these vectors and realizing that when we're talking about a plus b, we have a1 plus b1 down to an plus bn. That's a plus b. Well, that could easily be commuted because we know that addition of real numbers a1 and b1 can be flipped around and written like this. And that's actually b plus a as vectors. So we've proven it. If we fill in this side, we've proven it, or at least the sketch of the proof right here. And it all comes from commutativity of real numbers. Most of the results that follow in these properties are pretty easy to see. The textbook does a nice job of showing all the proofs, and I'll leave it at that. I think it's a good exercise to go through and write proofs for each of these properties just to confirm that they're true. But note that stepping into this realm of vectors and then later on matrices, we don't get all the properties that we're used to for real numbers. Commutativity of addition for vectors holds, luckily, because of the definition of vector addition. We'll see later on that something like matrix multiplication, which we'll define a few sections from now, does not have a matrix multiplication does not have a commutative property. The matrix A times the matrix B is not equal to matrix B times the matrix A. So we can't take these things for granted. We have to prove them every time we define these new objects. So I'll leave the rest of these to be proven as an exercise, or at least looked up in the textbook. But a lot of these are very obvious looking. Just remember to write out the components and make sure that that's the case. So that brings us into linear combinations of vectors. And this is where we're really getting interested in what's going on with these objects. A linear combination of vectors v1 to vk, k being some real number, in the real space Rn. So by the way, R1 is just the real number line. R2 is the plane, the xy axis that we're familiar with. R3 is three-dimensional coordinates. R4 is four-dimensional space, and so on, by the way, and n could be any value there. Anyway, if we have k vectors that are among that space, k not necessarily being equal to n, clearly, because we're different letters, and we have scalars c1 through ck, then a linear combination of these k vectors is given by c1 times v1 plus c2 times v2. Each of the c's are scalars or weights for the linear combination, and the vectors v are multiplied by those weights. So it's almost like you almost think of it as an average or some recipe combining v1, v2 all the way through vk to get some new vector in the space Rn. Okay, that's a linear combination of those vectors just by multiplying by a constant and adding them together. So let's look closely at this example. They ask us, well, they let us, or they have us let a1 equals 103, this vector. We have a vector for a2 and a vector for b. And they ask to determine whether or not b is a linear combination of a1 and a2. So in other words, what they're asking to interpret the language here is they're saying, is there some combination? Are there C1 and C2, which I will use a notation here, which are elements of the real numbers. So in the set of real numbers is the way to write that out thoroughly once. In the set of real numbers, not the space Rn, but just scalar real numbers, right? 5, pi, any scalar real number that we're familiar with. Are there C1 and C2 in the set of real numbers such that C1 times the vector A1 plus C2, so in other words, is there a linear combination of A1 and A2 that's equal to the vector B? And asking if there's a linear combination of A1 and A2 that equals B is the same as saying, are there scalars C1 and C2 that make this equation true? That's how we'll interpret that, because that, after all, is what a linear combination is. So now we just need to fill in the things we know. We're looking for C1 and C2 that might satisfy this. There might not be a C1 and C2 that satisfy this. So let's take it slowly and find out. So we know that A1 is the 3 tuple, or the vector 1, 0, 3. We know that A2 gets multiplied by its scalar C2 that we don't know yet, -2, 1, 1. Moreover, we don't know C1 or C2, and they may not even exist. We need to find out whether or not they can exist, and if they do, what they must be equal to. So when we look at this, we remember what scalar multiplication is. By the way, we're looking now at a vector equation. This is a linear combination of vectors on the left equal to a vector on the right. So this is our standard vector equation. And what we're asking is whether or not there's a linear combination, constant C1 and C2, that satisfy this. Well, remember scalar multiplication times a vector, and then the sum of two vectors. So it would look like this. If we start to simplify this, we have C1, 0, 3C1 in this vector, right? We multiplied by our constant C1, plus over here we have -2C2, C2, C2, each of those are multiplied by 1, equals 6, -1, 11. If we go further, we realize that we can combine this, or write the sum of these two vectors. So C1 minus 2C2 equals, is this vector. That's equal to, over here, 6. And then the second row is, well, 0 C1 plus C2. And that's going to be -1. And then at the bottom, we have 3C1 plus C2. And we have 11. So I wrote that suggestively. Each of these lines is actually an equation. In order for this to be true, given our definition of two vectors being equal, each component must be true. And each component really just represents, each component equation, that is, represents an equation, and this forms a linear system. So this is one way to go about determining whether or not C1 and C2 actually exist. It's solving this system of three equations in the two variables C1 and C2. So there's another way to do this as well. We could take this system and rewrite it as a matrix, but I think we see a pretty easy out for this. We already have one of these variables. C2 has to be -1. So we can plug that into either of the other two equations and see what C1 must be. So I'll do that by plugging it into this first equation. I'll work upwardly, which is a little bit of a difficult thing to see. But if I write in the line above that C2 is -1, I have C1 minus 2 times -1 equals 6. If you solve for C1 here, you have C1 plus 2 equals 6. So subtract 2 from both sides. C1 is 4. So this suggests that for the constant C2 equals -1 and C1 equals 4, that there is a linear combination, that we could produce B by combining A1 and A2 with these two multiples respectively against them. Now, the thing we haven't used is this equation down here. We could have used this equation in order to solve for C1, but it was sort of redundant. And this is where things get a little bit tricky, right? We want to make sure that whatever we choose for C1 and C2, this actually holds. If it doesn't hold, then we're not able to build this component out of A1 and A2, and the situation would fail, right? We wouldn't have C1 and C2 for which this is true. We're actually doing a lot of linear systems of equations work right here in front of us. And we're thinking about consistent and inconsistent systems by considering whether or not C1 and C2 work for all three of these equations, right? Well, the other way to check that it works is just to say, and so it's one way or the other, we could plug in C1 and C2 here and see whether or not this is true. I think we'll find that it is. Or we could just overall get the bird's eye view check of what's going on, which I think is worthwhile just to see how these things work out. So remember, we've got, I'll make a copy of this vector equation, and C1 is 4, C2 is -1. So let's write that down on the next page. So C1 is going to be 4. So we'll put a 4 here. 4 times this vector, and C2 is -1, so we'll just put a minus in front of this. And what we're doing is we're really checking, we're asking, is this now equal to the right-hand side, 6, -1, 11? And by doing this, we'll effectively check whether or not we've got the solution for all three rows, right? So on what we've got here is 4, 0, 12 minus, well, I guess we can write plus, and we'll just pass the minus in. We'll have -1 times -2 is 2, and then -1, -1. And I'll just start with the left-hand side to see whether or not it's going to be equal to the right-hand side. We add 4 and 2 to get 6. That checks out. 0 and -1 to get -1. 12 and -1 to get 11. And we have exactly the right-hand side. And this worked out. We found two constants. C1 equals 4 and C2 equals -1, such that A1 and A2 are linear combinations of B. To rewrite that in an interesting way, we might say this: 4 times A1 minus A2 is equal to B. This is our vector version of that linear combination. So let's keep this in mind. We see what we started with at the very beginning of this equation, right? We started here, right? And then we built a linear system of equations out of this. Well, we had this linear system of equations. Think about what its augmented matrix would be and compare that to these columns that we have. The columns in our given vectors, our linear combination of vectors being equal to a right-hand side, would match the columns that appear in this linear system of equations. So what we're dealing with oftentimes is we're going to start thinking about our linear systems of equations as linear combinations of column vectors when we start to find our solutions. So let me just write that down so it's very clear. I'll put maybe in a black ink up to the side here, that our augmented matrix, by the way, if we were going to solve that linear system of equations we came up with, our augmented matrix would actually be 1, 0, 3, -2, 1, 1, 6, -1, 11. And if we brought this to reduced row echelon form, remember this is the column for C1, column for C2, and that's our right-hand side next to that. If we reduce this to reduced row echelon form, we would come up with the same solutions that we had that we got through the linear system directly. We'll also find that this third row should be a row of zeros. It contributes nothing, and we solve for C1 and C2 via their own rows. So that is the connection to the augmented matrix we've already worked with. We're going to start thinking about taking these matrices apart and talking about their columns as individual components. And this is more or less summarized here, right? The vectors of the previous example form the columns of the matrix. This would be the matrix, the augmented matrix, written in vector form, right? A1 is our A1 vector. It's the coefficients that were times C1. A2 is the coefficients that were times C2, and B is the right-hand side, the elements of the right-hand side. So we write our linear system of equations or system of linear equations as a vector equation now, right? Where again, A1 is our column of coefficients, each of which is times a variable x1. Now x1 standing in place of c1, x1 and x2, all through xk are now the weights of this linear combination of columns. So a linear system of equations can be thought of as a linear combination of vectors where the weights are the variables x1 through xk. So that's our connection to the linear systems. And we'll often write these things because we're going to deal with these vector notations throughout the course. We'll often write it in this format. This is a really handy way to break things down. This would be, this highlighted notation is the vector form of our linear systems augmented matrix. So we'll write some of that down in coming examples. So this brings us to the next concept, and that's the idea of a span of a set of vectors. So if we have a set of vectors v1 through vk, so we have k of them, and they're all vectors in the real space Rn, n-dimensional real space, and the set of all linear combinations of v1 through vk is denoted the span of v1 through vk. In other words, all linear combinations literally means every scalar multiple times each one of these vectors and add it up. So there are infinitely many vectors in a span of vectors, right? Even if we just had one vector in here, we could have infinitely many scalars times it, 1, 2, 3, 4, so on. Those are all scalars times a vector, all the real numbers, and we'd have an infinite span here. So our set containing infinitely many vectors, but when we can add them, we're changing their directions as well. So the span of every element in the span of the vectors v1 through vk looks like this. It's some linear combination of the vectors v1 through vk, where c1 through ck are scalars or real numbers. So that's the idea of that. We can generate new vectors by adding up combinations of the vectors in our given set. So this is the basis for something that we'll use pretty heavily in the future. We're now just kind of putting the idea out there to define it, and we'll come back around to it as we progress. So let's have a look at this example. We're given two vectors, a1 and a2, and then we're given b as a third vector. They say that the problem tells us that the span of a1 and a2 is actually a plane through the origin in R3. So there's a bit to break down and explain there. They ask the question, is b in that plane? So to convince you that these two vectors do form a plane, let's go to a quick geometric interpretation of this. I'll draw this in, and then I'll get rid of it. So I'm not going to try to accurately draw these vectors in space. It's difficult to do this in a three-dimensional space, but here we're in R3. Clearly, we're in the three-dimensional coordinate axes. And A1 we'll say is, I don't know, some vector that's out here like this, and then maybe A2 is some vector like this with a slightly different magnitude. And A1. Any linear combination of these vectors is going to reside in the plane that these two vectors are actually in, right? So let me possibly draw the plane that these vectors are in. This could be coming out of the page or something like that. But anyway we combine these two vectors, we have 2 degrees of freedom. We can travel along A1 or along A2, but we're never going to leave the plane that A1 and A2 are in. And that plane passes through the origin necessarily because A1 and A2 both have their initial points in the origin. So that's how we know that this plane passes through the origin. It's in R3. The reason it's not three-dimensional space is because we don't have a third vector. We don't have a third degree of freedom to be able to move off of the plane that these two sit in. If you think about, maybe take your index finger and middle finger and just kind of arrange them in any way you want to, in a peace sign or kind of a twisted peace sign, And just notice that no matter how you arrange it, those two things, if you're careful about the fact that they should be starting in an origin, they're actually going to be in a plane. They're going to form a plane. So yeah, hopefully that is a helpful thing. Or if you take two pencils or a pen and a pencil, put one in together, it doesn't matter how you twist them, what angle you make with them, they're always going to be in some plane because they start from the same initial point. So maybe that's an idea worth seeing in person at some point. So anyway, 2 degrees of freedom in R3 means we're going to form a plane at most. So they tell us that the problem does tell us that this is a plane, so we can accept that that's the case. Now, what does it mean for B to be in that plane? Well, it means that we can combine one of A1 or A2 or some part of A1 and some part of A2 in order to get the vector B wherever it might be. So in other words, can we combine A1 and A2 in some linear combination in a way to form the vector B? And well, if that's the question, then really all they're asking is this: are there constants C1 and C2 such that C1 times A1 plus C2 times A2 is equal to B? And so we're saying this: are there such C1 and C2 in the set of real numbers? Are there C1 and C2 elements of the real numbers that satisfy this combination? Well, it's just like we did in the previous problem now. We say C1 is 1, -2, 3, plus C2. And we have 5, -13, -3. And this is all equal to the vector B, which is -3, 8, 1. Well, we know that we've already talked about this. This is more or less like saying this is the C1 column of coefficients, the C2 column of coefficients, and this is the right-hand side. So rather than convert this to our linear system of equations like we did in the previous example, I'm going to go straight to an augmented matrix and solve it the way we could have solved the other one, and just show the connection between columns of our matrices and linear systems, as well as the connection to these vector equations. So we have 1, 5, -3, -2, -13, 8, 3, -3, 1. So there it is. This is our augmented matrix for this system. And this is where this nice sort of enveloping connection between these topics. So we've got a 1 here. I'm going to leave that as my leading 1, and I'm aiming for reduced row echelon form. I think that's always the easiest thing to do. R2, or at least the easiest way to interpret solutions. Row 2 is going to become itself plus 2 times row 1. We want to get rid of that -2 with that leading 1 in row 1. Let's do the same for row 3 or something similar. It's going to be itself minus 3 row 1. So row 1 is unchanged. Just use its information to make these adjustments, to change the other rows. We have a 0 here. So then positive 2 times 5 is 10 plus -13 is -3. Third column, 8 minus 2 times -3 is 8 minus -6 is 8 plus 6 is 14. The bottom row, row 3, 3 minus 3 is 0. -3 minus 3 times 5 is -3 minus 15, so -18. And then 1 minus -3 times -3 is 1 plus 9 is 10. Okay, so now we need a leading 1 and a subsequent row. So let's go ahead and turn this into a leading 1. So we'll multiply by -1/3 on row 2. 1/3 row 2. We end up with 1, -14 over 3, 0, -18, 10. This is going to get a little messier, but we need to zero out this term. So we'll do row 1 minus, or equal to itself, minus 5 row 2. And similarly, we need to get rid of that negative 18. So we'll do row 3 is itself plus 18 times row 2. Now, that leaves us with a 1 here because the zeros aren't going to change anything. And we have a 0 because we got rid of that 5. And then negative 14 over 3 times negative 5. So let's see, that's 70 over 3 minus 3. 70 over 3 minus 9 over 3 is 61 over 3. You can check that arithmetic on your own. 1, negative 14 over 3. Things are looking good. 18 times row 2 added to row 3. That zeroes the negative 18 out. 18 times negative 14 over 3. Well, 18 and 3 cancel to a 6. 6 times negative 14 is negative 84. Negative 84 and 10 is negative 74. It really doesn't matter what that number is because it's not 0. Along this row, we see an inconsistency. This tells us that 0C1 plus 0C2 equals negative 74. That's asserting that 0 equals negative 74. In this case, there are no such C1 and C2 in the set of real numbers. Thus, so there's no linear combination that makes this true. Thus, B is not in the span of A1 and A2. By the way, anytime we have two vectors that we're spanning with, it forms a plane. If we're spanning with one vector, it forms a real number line. If we're spanning with three vectors, it forms a three-dimensional, at most it forms a three-dimensional space. Same thing for two vectors. At most they form the plane or two-dimensional space. It's not in the span of this, i.e., that is, B is not in the plane formed by that span. Span of A1 and A2. So that settles that. It's really no different than the question before. It just has a geometric interpretation to it. So the main takeaway of this is that we're going to start thinking about our matrix columns as columns of coefficients or vectors in a linear combination of vectors being equal to a right-hand side B. So that's one way that we're going to like to decompose matrices. And that's really the end of section 1.3.